get parabolas, or what we call quadratic functions. And the idea of a quadratic function, it's like a quadratic equation, except we're not always setting it equal to 0. Something like this. Oh, that works. So this is what's called a quadratic function. Now, what we're going to be interested in is a number of things. We want to try to graph these things for one, and they're a very powerful tool. We use lines to come up with models for certain relationships or phenomena, like wages, for example. As you getting paid an hourly wage, the more hours you work, the more earnings you get, and that tends to follow a line. What's really great about these is they're very powerful for finding maximums and minimums. And the reason is this. When we graph functions of this type, you'll get either this or you'll get something like that. So the graph of this function, this lowest point and this highest point, sort of where the function kind of sprouts out, that's called a vertex. And if we can model some kind of relationship using one of these parabolas, and that's what these are called, well, we can find out the minimum of something or the maximum of something, and we'll take a look at an example of that later tonight. So let's take a look. What we want to do first is look at what we're going to call the vertex form of a quadratic function. And we're going to derive this from scratch. So we're going to start out with kind of a generic quadratic function, a simple one, relatively. So it's going to look something like this. Now, the simplest one we could ever get would be equals x squared. We're going to throw an a in here. And if you remember from our section on transformations, if a is bigger than 1, you'll take the standard function of x squared and you'll stretch it vertically. If a is less than 1, then you'll squish down this parabola like so. So we're just putting this constant here. Another thing with this a, remember, if a is positive, we get an upward facing parabola. But if a is negative, we reflect this over the x-axis and it flips. Anyway, just a little review of what we looked at with transformations. So we're going to start out with this though. Now, as you might recall, let's say we want to shift this in some direction. So to do that, we can do minus h. So this means our parabola will do something like this. Now, when we did transformations, we assumed h, or when we did transformations, we used the letter c. We always assumed it was greater than 0. This h, we can play around with it a little more. If h is greater than 0, then sure enough, we transform over here. If h is negative, minus a negative becomes a positive. It actually becomes x plus and then the positive version of h. So if you have h was -3, x minus -3 becomes x plus 3. So this h could be positive or negative. If it's positive, it's just like the transformations we saw before. X minus a positive number shifts you to the right over to that positive number. But maybe h is negative. And so when you simplify it down, you'll get x minus this h. Since h is negative, you get x plus 3. And so that means you end up transitioning over here like so. So just something to keep in mind. So we can go from here to here. This means we're going to translate this parabola somewhere to the side. And then we're going to do this. We'll add k. So we have our parabola. We shifted it horizontally over here. And then we're going to lift it up to k. We're going to get something like this. Now again, this k, if we follow our transitions or our transformation, this means we always kept k positive or c positive, so we just moved it up k or c units. Now in this case, k could be negative, and you're adding a negative number. It's the same as subtraction. That would actually put you k units down here. But let's just leave it like this for now. So I'm kind of assuming this is positive and that's positive, but they don't have to be. So what does this give us? Well, this means this vertex is located at h, comma, k. And so this is the vertex form of our parabola. So, for example, let's say we're going to do this. If we have and we're asked to find the vertex of this parabola or this quadratic function. Well, this is our h, and we're always subtracting h. This is our k. So we're always adding k. So this means the vertex, h comma k, is 4. See, it's a positive 4, comma 1. We always subtract h. We're always adding k. Now let's try something a little different. Now what we can do is we can rewrite this so it's x minus h and then a plus k. And the way we can do that is remember that a plus sign could come from a double negative. And then subtraction, we can add a negative. So we'll always subtract h. H will be -2. We're always adding k. K will be -7. So our vertex is -2, -7. All right. Now, we saw the original form for a quadratic function, and it was this function. Now, how can we relate, or really, how could we figure out the vertex from this form? And how do we get it to the vertex form? Because when this is in the vertex form, well, it's not too bad to get the vertex out of there. But how do you get the vertex out of this? Well, we're going to try to do it. We're going to try to put this in vertex form. So what we can do, we'll factor out A. And I'm only going to factor it out from these first two terms. Now this may look kind of strange, but if you want to check the work, if you distribute A to each of these terms, you'll get ax squared, and then get A above, A below, the A's will cancel, you get bx back. So we're going to complete the square. We're going to use kind of a slick trick for doing this. Completing the square, we take the number on the x term, divide by 2. What you get is this. So that's what we're going to use to complete the square. Now, to do this, we need to square this, add it to both sides. Well, in this case, there's another way of doing it. We don't have to actually add it to both sides. We can still keep things balanced if we do something else. So first, let's square this. Now, you might not remember this from the rules for exponents, but when you have a square like this, it gets distributed as an exponent to the b, to the 2, to the a. So you get b squared, 2 squared, which is 4, and then a squared. This gets distributed as an exponent. So it ends up ending up like here, here, here. Anyway, we're going to do something kind of interesting with this. Now you might say, hold on. If you're adding something to this side, you've got to add it to this side. I'm going to say, no, you're absolutely right. But check this out. If I add this and then subtract it, something minus itself is 0. So all we've done is included 0. Well, that seems kind of silly, but check this out, it works. So f of x, what we're going to do in this f of x is we're going to factor out, we're going to pull this out. So the way you can think about this, we could distribute a to each of these 4 terms, and then put parentheses around the first 3. And then factor a out of the first 3. So we can, and I'll go through the steps here. Let's see, there we go. You could do something like this. Ax squared plus a b over ax plus a b squared 4a squared minus a b squared 4a squared. And then this plus c was out here. It wasn't in the parentheses, so it doesn't get an a distributed to it. And then we can put parentheses around these just because we can. And this is a completed square. Well, almost. We've got to factor out the a. And this is actually a completed square. We started with this, and we divided this by 2 to get b over 2a. Square b over 2a, you get b squared over 4a squared. So we can rewrite this as a completed square. And there's some cancellation here. You have an a squared and an a, so this will become b squared over 4a plus c. Or you can write this a little differently. And notice that I changed the plus to minus a negative. We always subtract h. And we always add k. So this is what we figure out. We come up with formulas for h and k. And there's actually a simpler way to do k, but I'll go over that. So it turns out h is negative b over 2a, and k is c minus b squared over 4a. Now here's the point with this. Remember, we started out with ax squared plus bx plus c. And we did some pretty crazy tricks. This funny thing, the way we completed the square, and as far as I know, we're not going to ask you to do that on a homework assignment or a test. Maybe. We'll see. Anyway, well, let's say we don't want to have to do that every single time. Well, here's a formula for h in terms of b and a that we could just read off of the original function, ax squared plus bx plus c. Here's a formula for k. There's the a, there's the c, there's the b from ax squared plus bx plus c. So if we just know these formulas for h and k, we don't have to complete any squares to figure out the vertex. We can just use these formulas. In fact, we can make this a little easier. Check this out. Let's put in f of negative b over 2a. What happens? We get a. Now, negative b over 2a is what x becomes, minus negative b over 2a. That's not minus negative b over 2a. Squared plus c minus b squared over 4a. Well, what's happening? Minus and minus, that becomes a plus. Well, here, I'll write it for your notes. So we take this, it becomes a plus. And this right here, well, that just becomes 0. So all we get is c minus b squared over 4a. And that's just k. So if we take h, the x-coordinate of our vertex, and just plug it back into the function, we get k. So this is why the text uses the formulas that it does. So for the vertex, hk, and again, we're not in vertex form anymore. We're in the form of a quadratic function, something like this. if we're in this form, h is negative b over 2a, k is f of negative b over 2a. Whatever that happens to be. And that's it. That's how we find the vertex. So let's take a look. Let's see an example here. So let's say we have this. Now let's say we want to find the vertex for this. Now again, not standard form, but vertex form, we just had to look for h, look for k, and read them right out of the whatever the function was. You might have to turn like an x plus 3 into an x minus a negative 3, or turn a subtraction for k into plus a negative for k, but you could read them out of the function. Here we got to identify first a, b, and c. A is negative 1, B is 2, C is negative 2. So once we've done that, H, negative B over 2A, or negative 2 over 2 times negative 1, or minus 2 over negative 2, or minus negative 1, or just positive 1. Now for k. That's f of negative b over 2a. But we found out what negative b over 2a is. It's 1. So f of 1. That's negative 1 squared, 2 times 1, minus 2. Or negative 1 plus 2 minus 2, or just negative 1. So that means the vertex and that's going to be the vertex. All right. Well, the next thing we're going to be asked to do is put all this together. Let's try to graph a parabola. So to graph this, what we're going to do? Well, we want to try to figure out if it opens upwards or downwards. Now, this sorts itself out as we plot the points that we're going to plot in a little bit. But just for reference, if little a is greater than 0, it opens upward. Little a less than 0, it opens downward. So that's the little a that we're talking about. Then we want the vertex. This is sort of that point where we get the minimum or the maximum, which is going to be important shortly. It's also kind of where the parabola sprouts out from. And we saw h, negative b over 2a, k, f of negative b over 2a, whatever this turned out to be. Then we want the y-intercept. The way you find the y-intercept just compute f of 0, and that will give you a y-intercept of 0, comma y. Now the x-intercept gets a little complicated. In this case, we set f of x equal to 0, and we solve for x. And so we tend to get, we put it this way, we get 3 results. We could get 2 x-intercepts. There's an x1 and an x2. Each one has a y-coordinate of 0. We could just get 1 x-intercept, some x comma 0, or we can get nothing. We can get 2 intercepts, 1 intercept, or no intercepts at all. Well, let's talk about how we can find these intercepts, and then we'll do an example. So you can solve this like so. This is what our f of x typically looks like. And there's 2 ways you can do this. You can do factoring, or, and this is really kind of a go-to, quadratic formula. Remember, we're setting this equal to 0 and solving for x. Now, the number of intercepts we get depends on this. This is called the discriminant. And if you notice, it's the body, it's the insides of that square root. And there's 3 things this typically becomes, or it falls into 3 categories. This will be a positive number, it could be a negative number, or it could be 0. Now, if it's a positive number, you get negative b plus or minus some positive number. And this is where you get the 2 x-intercepts. You get an intercept for the plus, negative b plus whatever the square root came out to, divided by 2a. The other one will be negative b minus whatever the square root came out to, divided by 2a. So when you get this, you're going to get 2 x-intercepts. And so an example of what that might look like. Something like this. There's an x-intercept, and there's a second x-intercept. And this is when this is positive, it's greater than 0. Now let's say it's actually equal to 0. What happens there? Well, in this case, this entire square root becomes 0. The square root of 0 is 0. So plus or minus 0, you're adding or subtracting nothing. There's nothing there. So this effectively just goes away. You just have negative b over 2a. And that's the x-coordinate for your x-intercept. So what that means, you might get something like this. and this is just, again, kind of a generic example, but the vertex, you might have noticed this negative b over 2a, when this becomes 0, it seems kind of familiar for an x-coordinate. Well, it'd be the x-coordinate of your vertex. And in this case, the vertex only contacts the x-axis at this one location, negative b over 2a. So how do you end up with no x-intercepts? Well, in that case, b squared minus 4ac is less than 0. Of course, that means it's negative. The problem is you have to take the square root of this. And unless we're dealing with imaginary numbers, and for this section, we're not. Since we're not doing anything with imaginary numbers, we can't take the square root of something that's negative. No way. So that means this isn't possible. That means the x-intercepts, they're not possible. That means you have no x-intercepts. So what does that look like? No x-intercepts? Well, what that would be something like this. There's just a generic example. But you have a parabola floating in one of the quadrants, opening up, but never reaching the x-axis. Or it could be doing something like this. You could have one like this. But in either version of these, the parabola never contacts the x-axis. There are no x-intercepts. So that is, 3 possibilities. So something we might be asked to do is graph one of these. So let's say we have something like this. Well, first off, we can identify A, B, and C. Well, we don't really need to know C, but for completeness sake, we'll put it up there. These are going to be important for our formulas for vertex. So just as a note, and again, we're going to figure this out by plotting the points, but we can just note that A equals 1. What's greater than 0? It's positive. When A is positive, we have an upward opening parabola. So if we graph our points and we get one that's downward, we want to take a look at our graph, maybe look at kind of the points we got, make sure we did everything correct. All right, vertex. H, negative b over 2a, or negative 2, 2 times 1, or negative 2 over 2, negative 1, or 1. So for k, we just plug in 1 into f. So we get 1 squared minus 2 times 1 plus 3, 1 minus 2 plus 3, negative 1 plus 3 is 2. So our vertex, h comma k, is 1 comma 2. I'm going to write that off to the side. There we go. So that's our vertex. Let's look for the y-intercept. Well, here we just compute f of 0. And there we are. So f of 0 is 0 squared minus 2 times 0 plus 3. 0 minus 0 plus 3, or 3. So 0 comma y is 0 comma 3. So I'm going to put that off to the side. There we go. Now we need to find the x-intercept. And for this, I'm going to use the quadratic formula, and that's where you're going to want to know a, b, and c. You want it for that. So for the x-intercept, well, that's your quadratic formula. And let's recall, a was 1, b was -2, and c was 3. Looking back at the formula, or the function from the beginning. Well, beginning of this example. So we've plugged these into the letters. And we notice something. As we're doing this computation, we're watching what's happening in the square root. The problem is we're trying to take the square root of a negative number. And that, in this section, we can't do. So what that's going to mean, since we can't do this, we're not going to be able to have any x-intercepts. So for this one, the x-intercepts, they're a no-go. So what do we have with the graph or parabola? We have a vertex, we have a y-intercept, and we know that it's upward facing. So let's put this together and try to graph it. So the vertex was 1 and 2. So that puts that right here. So our parabola is going to sprout up from this vertex. Now we know it needs to pass through 0, 3. So it's going to do something roughly like this. So that would be a very rough drawing of our parabola. And then we could, label this point. Oh, I think I made a mistake. It's 1, 2. Oh dear. I did 2, 1. Let me try again. 1, 2 is right here. That looks a little better. There we go. And so that's just a rough sketch of our parabola. And notice, since it's pointing upward and we're starting here, it never crosses the x-axis. There are no x-intercepts we get the graph. All right. Let's see this. So let's say we do this one. Now again, we can identify A, B, and C. So taking a look at this one, again, A is 1, which is greater than 0. So it's upward facing. Now, for the vertex, H, negative B over 2A, or negative negative 2 over 2 times 1. And we've kind of seen this one play out already. This will come out to just be 1. So f of 1, that's going to be k, or f of negative b over 2a. And so we get 1 squared minus 2 times 1 minus 15, or 1 minus 2 minus 15, and that comes out to negative 16. So the vertex is 1, negative 16. Now, you can kind of look ahead here. Using this information, this was upward, and the vertex is, this is 1, this is negative 16, but the vertex is down here, because that's where it's going to be. And this is upward. It's going to have to cross the x-axis twice. So we can expect to have 2 x-intercepts. So we're just looking ahead. Well, let's look for that y-intercept. So that's f of 0. That'll be 0 squared minus 2 times 0 minus 15, or 0 minus 0 minus 15, or minus 15. So we get a y-intercept of 0, negative 15. Now for that x-intercept. Looking ahead, we can see we're going to get 2 x-intercepts with this one. So we remember A was 1, B was negative 2, C was negative 15. I'll double check that. Yeah, we got it. So x, negative b, plus or minus the square root, b squared, minus 4ac, divided by 2a. We plug in a, b, and c. And there we go. So let's simplify this. Negative and negative becomes a positive 2. 4, negative 2 squared, negative 2 times negative 2 is 4. Negative times negative is positive. So we're going to plus here. 4 times 1 times 15, that's 60. Over 2. Or what we're going to get is 2 plus or minus the square root of 64 over 2. And that works out really nice because the square root of 64 is 8. So this is where we get the two x-intercepts. This turned out to be a positive number. Square root of a positive number for us is going to be, well, plus or minus that number. So it breaks down into two intercepts. One for the plus, one for the minus. So this will become 10 over 2, negative 6 over 2, or 5, and negative 3. So the two x-intercepts we're going to get. And remember, with the x-intercepts, the y-coordinate's always 0. These are the x values, y-coordinate or y values always 0. And there we go. And we also know this is a upward-facing parabola. So let's graph it. Here's something roughly like this. It's kind of a rough graph. So let's say negative 16 is down here. Here's negative 15. Negative 3, positive 5. So we have a vertex. Oh, it's a 1 here, we need a 1. So at 1 and 16, negative 16, we have a vertex. 1 and negative 16. So we've got that point. There's a y-intercept at 0, negative 15. So we've got that. X-intercept, 5 and 0, negative 3 and 0. So putting these together, what we're going to get for a rough graph, very rough graph, is something like this. Ooh, barring artistic license. Okay, not as much artistic license. Even if we didn't know this was upward facing, by connecting these points, going left to right, we're still going to get upward facing parabola. So that's graphing parabolas. The last thing to go over for this section is applications. And I mentioned at the beginning, what's really powerful about this section is you can use it to find minimums and maximums. Now, let's say we have this. We have 600 feet of fencing. And what we've decided to do is we're going to use this fencing to fence off a garden. Now, the way we're going to do this is we've got a river. And we're going to fence a rectangular garden, not a half circle, not a triangle, a rectangular garden where we use all 600 feet of that fencing. Now, here's the thing with this problem. You might say, well, there's only one way to do this, right? I mean, not only one way, there's probably lots of ways. Well, there are lots of ways you can use up all 600 feet of this fencing. There is. But we want to use the fencing, come up with a width and a length. We're going to have some widths, 2 widths, and 1 length. We want to come up with the width and length that maximizes the area of this garden. So let me show you how this might not work out. So let's say we have a river. And let's say we did this. We did a garden like this. Let's say this was 50 feet. This would be 225 and 225. Let me get a calculator here real quick. Pardon me just a moment. What we're going to see is if we compute the area, well, or length, this dimension times that dimension. This area comes out to be 11,250 square feet. Now let's say we chose the lengths and widths differently. And keep in mind, if we add these together, we're going to get, let me double check this here. Oh, that's not going to be 600. Let's say, I'm sorry, I made a little mistake. 275. 275. Yeah, that's better. So 275 times 50, 13,750 feet squared. Now, we could do this differently, though. There's a river. A really long garden like this. And we can make this 500, make this 50, make this 50. This adds up to 600. This will add up to 600. So in both cases, we've used up all of our fencing. This comes out to 25,000 square feet. So here's the issue. In both of these scenarios, we've used up all 600 feet of our fencing. But depending on how we chose the width and the length, we get different areas. So is there some choice of width and length that gives us the largest possible area for our garden? And so that's what we're going to try to figure out. So again, what I recommend with these types of problems, break them down into knowns and unknowns. It's also what the text recommends, but it's a good way to go. So first off, what do we know? Well, we have our picture. We know what this is supposed to look like. We know that we have 600 feet of fencing. This will become important very soon, but we know we have this, 2 widths, 1 length. The other length of our garden is bordered by the river. We also know this is rectangular, so the area is length times width. If we were doing like a half circle garden, we would use a different formula, like 1/2 the area of a circle, or 1/2 pi r squared. So that's what we know. So what do we not know? Well, the length and the width. So we have 2 unknowns here. And in these types of problems, we want to reduce it down to 1 unknown. Is there one that stands out? And what we're going to find out is we can come up with a way of defining length in terms of width. So if we discover width, we will automatically know length. That's going to come up in step 2. So for step 2, we have what we know, we have what we don't know. And it's what we don't know. When we discover what we don't know, we want to bring that out into reality. So let's call length, bring it into the world of math. Let's give it a variable L. And width, bring it into the world of math. Make it a variable W. And again, variables, they're numbers, actually. We just happen not to know which ones just yet. Now, in step 2 of this process is where we want to reduce the number of variables from 2, L and W, to really just 1. And the way we can do that, and this is a little subtle, let's go back to that picture. There's our river. There's W, W, and L. So, can we reduce the number of variables to just 1? That's a big goal for these types of problems. Well, there is a way. Remember, the total fencing is 600. So that means if we add these 3 sides, whatever they happen to be, I mean, who knows, they better add up to 600. That's what we're going to get. And this is where we can come up with a formula for length. We want to describe length in terms of width. Well, all we got to do is solve for length. Subtract 2W from both sides. So here's the breakdown. W's ultimately the unknown now. So this is what we've got. W, no idea. That's the big mystery. But if we can solve this mystery, we automatically know length, because length is just 600 minus 2W. So that means when we go back to our picture, everything can be in terms of W. So instead of L, 600 minus 2W, we've done it. Everything's in terms of 1 variable, we don't have 2. And for these types of problems, again, that's a big goal. Whew. So now that we've got that, we get to step 3. We're going to try to come up with an equation that's going to help us solve our problem. This is an equation, certainly, but it's an equation to establish a relationship between L and W so we can eliminate L. So it is an equation, but it's one that helps us reduce the number of variables from L and W to everything in terms of W. This equation I'm talking about in step 3, this is the big one. This is the one that lets us solve the problem. And we go back to the area. That's what we're interested in. We want to try to maximize the area, and that area is L times W. Oh, wait a minute, we can write L in terms of W. So now we're on familiar territory. We have an input and an output. Here we have 2 different inputs, and we really haven't talked about that. You deal with that in Calculus 3. But now we're in familiar turf. 1 input, 1 output. Okay, the input's repeated, but that's okay. It's the same type of input. And then we have an output instead of 2 types of inputs. And we can simplify this, distribute your W. Or we can write this here we go. Now what's really neat about this equation, this gives us the area of our garden. Gives us the area of our garden. So if we put in a width, we'll get the area. Now if we ever want to find the length, just plug in that same width and we'll get the length also. Now let's take a look at this equation though. This is step 4 where we really get to solve it. Now let's break this down into A, B, and C. So A is -2, B is 600, and this one doesn't have a constant term. C is 0. So what this is, note that A is -2, so it's less than 0. Notice W squared and W, this means we have a parabola. A is -2, it's less than 0. So it's downward facing. So here's the cool thing with parabolas and minimum and max. Because this is downward facing, the vertex, that becomes the highest point on this parabola, or the maximum point on this parabola. So if we can figure out the vertex, and remember, this is representative of the area. So if we were to graph this function, input, output, it's doing something like this. This vertex is the maximum area. And this here, this is the width for that max. So there we go. So all we have to do is figure out the vertex, because this is the x coordinate or the w coordinate of this vertex. Let's find this vertex. So for here, the w, or our h, negative b over 2a, or negative -2 over 2 times -2. Oh, I'm sorry, 600. B, forgot. Negative b over 2a. Or negative 600, -4. And this will simplify down to 150 feet. So what we've got here is we know the w coordinate that gives us the largest area. Now, just to figure it out, I'm just curious, what's the largest area? We're not asked to find this, but let's see. So it would be A is, let's see here. -2, 150 squared, plus 600 times 150. Let's see here, 150 squared. It's going to be negative 45,000 plus 90,000 or 45,000. So it turns out when we make the width 150 feet, we're going to get a garden with an area of 45,000 square feet. Now remember when we did these calculations earlier, we got a calculation where we had something like this. 275, 275, and 50. And when we computed the area, we got 13,750 square feet. We did another version of this. Where we had our fencing like so. We got 25,000 square feet. So 13,750, 25,000. But if we let the width be 150, we're going to get 45,000 square feet. That's a lot more. Well, anyway, hold on. So that means we need to find the length, though. So just to kind of update what's going on, we did find our vertex. The maximum area is 45,000, and that happens with the width of 150 feet. So that's what we figured out. We do want to find the length. Remember, the length was 600 minus 2W. So for us, since we know we want a W of 150 because that's what maximizes the area, 600 minus 2 times 150, or 600 minus 300, or 300 feet. That's going to be our length. So when it's all said and done, the largest garden we can come up with, 150, 150, 300, and this will have an area of 45,000 square feet. So it does matter how we choose our width and choose our lengths. It can matter dramatically. So the power of this, to find the maximum, we use the property of the parabola. We have a downward facing parabola. The vertex is a max. And so we can use that fact to come up with the maximum area. And that's the power of using parabolas. One more thing to show you. Axis of symmetry. An axis of symmetry cuts a parabola in half down the middle. So if you have a parabola, say, floating around like this, with a vertex, if you cut this parabola in half, you're going to cut right through that vertex. And so this is x is negative b over 2a, and this is f negative b over 2a. So one of the questions that's going to come up in this section is find the equation for the axis of symmetry. Well, that's it. It's a vertical line. X equals negative b over 2a. And that's it. So that's it for this section. If you have any questions, let me know. Other than that, have a wonderful evening.